Welcome to NASA Science Live. This is your opportunity to interact with NASA experts and have your questions answered in real time. I'm your host, Tahira Allen. Today, we're exploring NASA's Juno mission, which has been orbiting Jupiter for almost 8 years. This has given it the unique opportunity to study two fascinating moons, one boasting lakes of lava on its surface, and the other thought to have a global liquid ocean hiding beneath its icy crust. Let's dive into the worlds of Europa and Io. Earlier this year, the Juno spacecraft conducted two ultra close flybys of Jupiter's volcanic moon Io, capturing a wealth of data and the highest resolution images of its surface in over 2 decades. These flybys are the closest that a mission has come to the surface since a visit by the Galileo spacecraft in October 2001. The maneuvers have allowed Juno to study the most volcanically active world in our solar system, which is also only a little bit larger than Earth's moon. Io is caught in a tug of war between Jupiter's powerful gravity and the smaller pull from two neighboring moons. This constant stretch is churning its insides, creating volcanic eruptions and lakes of lava that cover its surface. Now, if Io is the world of fire, you can think of Europa as the world of ice. And just earlier this week, scientists released a new estimate for the amount of oxygen that's being produced on this moon using data collected by Juno in 2022. Europa is the destination of our upcoming Europa Clipper mission that's launching later this fall and is a world that is of great interest to astrobiologists searching for signs of life in the universe. Scientists are almost certain that a vast ocean lies beneath Europa's icy shell, as well as other ingredients for life as we know it, like chemistry and energy. These new findings are helping us better understand if this icy moon has conditions that could be favorable to life. Let's see how scientists are using Juno data to unravel the mysteries of these fascinating worlds. Now, if you have questions throughout today's show, you can submit them using the hashtag AskNASA on social media, or you can drop them directly into the comment box wherever you're watching. Today, we're joined by two special guests who are going to be answering those questions live on air. We have Dustin Buccino, a NASA Juno mission engineer and scientist. Welcome, Dustin.
Thank you. Thank you for having me.
And Dr. Rosaly Lopes, a Volcano expert and NASA Juno associate team member. Welcome, Rosaly.
Thank you, and it's a pleasure to be here.
And thank you both so much for being here with us today. Can you start off by telling our viewers a little bit about your individual roles with the Juno mission? Dustin, let's start with you.
So what I do, I have two hats on Juno. My first role is the gravity instrument engineer, so I'm responsible for collecting all of the data and processing the data for the gravity science investigations we do, which is measuring the interior structures of Jupiter and its moons. I'm also a part of the science planning working group where we take all of the science objectives that we want to accomplish on any given orbit around Jupiter and combine them into a cohesive plan that we can give to the engineering team to execute.
And what about you, Rosaly?
I also have two hats. The first is my job here at JPL is Deputy Director for the Planetary Science Directorate, and Juno is one of our missions. So the success of Juno is very important to me. But the other, which is actually more fun, is a collaborator on the science of Juno. Scott Bolton, the PI of Juno, and I worked together back on Galileo days. And because of my expertise on Io, he invited me to help out the Juno scientists, and that's been great.
You know, Rosaly, talking about your expertise with Io, I know you've done a lot of research on this moon, even winning a world record for the amount of active volcanoes you've discovered. Can you tell us, why is NASA so interested in this world?
Io is a really interesting and rather weird, unique moon. It's the most volcanically active object in the solar system. We may think that the Earth has a lot of volcanoes, but Io has bigger volcanoes, bigger lava flows. They're erupting all the time. Gigantic plumes, volcanic plumes above the surface, and we think that some of the eruptions on Io are very similar to the eruptions on Earth in the Earth's early history, like hundreds of millions to billions of years ago. And even the composition of the lava may be very similar to primitive lavas on Earth. So looking at Io gives us a way to look at the early Earth and study eruptions that don't exist anymore on Earth.
That is so cool to think about. And so I understand too, it's due to Io's unique position in this Jupiter system that really has to deal with its volcanoes and its inner mechanics. And so, Dustin, I know you focus a lot on the Jovian system. So, again, Jupiter, its rings, its moons. Can you explain the significance of Io and Europa within this system?
So Io drives so much of what's happening in the Jovian system. Uh, as Rosaly mentioned, Io has a lot of volcanoes, and it erupts and creates these plumes, which are then create the atmosphere of Io. This atmosphere gets stripped away because Jupiter is rotating very quickly and has a large magnetic field. And Jupiter's magnetic field actually takes these particles that are being erupted by Io and emits them and ionizes them into the magnetic field. And once they are ionized and charged, they get to move around along these magnetic field lines. And they create these large amounts of plasma that then move around the Jovian system, creates radiation hazards for when we fly our spacecraft through there. But also, these particles then get, in the right position, they get moved along the magnetic field lines into Jupiter itself, and they hit Jupiter at the poles and create these massive auroras. Just like we see on Earth with the auroras, there are auroras on Jupiter that are even larger, and it puts a lot of energy into the Jovian atmosphere through this mechanism, and it really is a full circle approach to this.
And so I want to now pivot a little bit and talk about Europa. So just this week, NASA released new science from Juno's 2022 flyby of the moon. And this data indicated that the ice covered moon generates about 1,000 tons of oxygen every 24 hours. So that's enough to keep 1 million humans breathing for a day. Dustin, what is the key takeaway here?
So the key takeaway here is really, Europa is producing oxygen. And one of the interesting things about Europa is that the surface is ice. And underneath that surface, we believe there is a large liquid water ocean. And on Earth here, where there's water, there is life, and we believe that could be the case on Europa. So we want to find out, how habitable is Europa? Now, this paper looked at a very interesting way of figuring out how much oxygen production there is when these same charged particles that I just talked about that are moving around the Jovian system impact that ice on Europa. It splits the ice, which is composed of hydrogen and oxygen combined, H2O. It splits it into hydrogen and oxygen. And some of that oxygen can propagate through the ice into the ocean of Europa. And that creates the potentially conditions for life.
I mean, just some fascinating workings going on these two moons. And we have a ton of questions coming in from our viewers online right now. So let's hop right into this Q&A. As a reminder to those watching live, you can submit your own questions for Dustin and Rosaly using the hashtag AskNASA on social media, or you can drop your question directly into the comment box wherever you're watching. All right, our first question is from Andrew K. Tyler on Facebook, who asks, where will Juno go after Io? Dustin.
So Juno is continuing to orbit around Jupiter, and every time we orbit, what Io did to our orbit was actually when we flew by Io in December 2023 and in February of this year, it actually shrunk our orbital period. We were in a larger orbit, and now Io, we did when we fly by that close, it alters Juno's trajectory, and so we're actually going to shrink our orbit, and so we're going to be by Jupiter faster than we used to be, and we're going to be taking measurement of Jupiter to understand its interior structure and its magnetic field, and all these particles that occur close in.
And so, as a follow-up, we have Ridman on YouTube who asks, we've been studying Io with Juno. Are there any ice volcanoes on Europa, Rosaly?
Oh, good question. Yes, we have seen features that can be interpreted as ice volcanoes, or we call this cryovolcanism because it's a cold volcanism. Essentially, volcanism is the process that brings material from the interior to the surface. So if your interior has magma like Io and F, then when it comes to the surface, that molten rock will be lava. But because Europa has liquid water under its ice crust, what comes to the surface is, either a plume of vapor or sort of slushy ice. You can think of it that way. And there have been a number of studies, even some evidence showing that plumes may be erupting from Europa. But we haven't found that that proof yet, and that's one of the things that Europa Clipper would be looking for: both evidence of cryovolcanoes on the surface and also plumes coming out of the surface.
And so, while we're on this topic of Europa, we have Ridman on YouTube who asks, is Europa pulled like Io with this gravitational pull, Dustin?
Yeah, so the mechanism that we talked about on Io, which is this what we call it tidal heating, and so the orbit around that Io and Europa take around Jupiter is not perfectly circular. It's off by a little bit, and so when the moons get closer to Jupiter, they are subject to what we call tidal heating. So the moon is essentially being pulled by Jupiter and squished almost, and that creates some heat, and that heat creates on Io the molten rock that we see in the volcanoes, and on Europa, which is farther away than Io, and so it's not as large of a magnitude of effect, but it's still there, and that tidal heating creates the liquid ocean that we believe exists under the crust.
That's incredible. And so we have Benjamin Wilson on Facebook who wants to know, how are we going to get under this icy ocean, under this ice to the ocean of Europa? And will we be able to do it remotely? Dustin, do you want to take that one?
So there are ways that we can look under the surface without having to go there. We would obviously love to go there and just look at the water and look at samples, but we can do what we call remote sensing techniques to sort of look under the surface. So the Europa Clipper spacecraft and Juno have instruments that are able to do that. So what I work on is the gravity science, and so that's measuring the interior structure of these moons and measuring this tidal heating effect that occurs. And we can do that by essentially measuring the position of the spacecraft. And we measure the position of the spacecraft very precisely by measuring the Doppler shift to Earth on the radio signal. And from doing that, we're measuring essentially the spacecraft's position, velocity, and acceleration, and that gives us how much gravity was experienced. And so if you're standing on the surface of Earth, you're being pulled by all the particles around you all the way to the center. And so if we measure this gravity field on a global scale around the two moons, we can actually determine what the interior structures look like and how much liquid there is relative to solid, and what kinds of solid, what's the density of the solids. Other instruments, such as Juno's microwave radiometer, are able to look a little bit below the surface to see differences in the ice at depth. And missions like the Europa Clipper will have an ice-penetrating radar to look below the surface as well.
So we're talking a lot about how we're going to be studying this moon, but Rosaly, can you give us an idea of why Europa? Why is NASA so interested in going to this ice-covered moon?
We're very interested in Europa because it's what we call an ocean world, and Europa's ocean may actually have life, is one of the most promising places in the solar system for life. As we were saying before, there is this tidal heating, and so Europa's interior also suffers, though to a much less extent than Io, from this tidal heating. There may be volcanism in the deep interior of Europa. If you have water, you have heat, energy. Those are some of the ingredients that you need for life. And the Galileo mission actually was the mission that found that Europa had this liquid ocean under an ice crust, and became very, very exciting.
Well, it's so exciting again too to think that we're now, months away from launching back to studying this moon with Clipper. And I want to take us back to Juno now. So we have Lidity on YouTube who asks, how did Juno manage to function way past its intended lifetime? Dustin?
So Juno was designed to last a certain number of orbits around Jupiter, and we've lasted a lot longer than that. Um, Juno is a very well-designed spacecraft. We designed the spacecraft to go to this intense environment around Jupiter. It has a vault that protects all of the electronics from Jupiter's radiation in the space environment, essentially bringing what would be a death sentence to a computer and preventing it from being hit by all these particles. And so Juno has been we fly the spacecraft very well and safely, and we keep monitoring and watching for these effects. And it's all a matter of the engineering and how well it was put together. And so it's a very well built spacecraft, and we're seeing it last longer because of the way we fly it and because of the design with the radiation vault.
And so I have a great follow up really quickly. Muhammad Ali on Facebook who wants to know, what is the velocity of Juno in orbit?
Okay, so Juno is in what we call an elliptical orbit. It comes in very close to Jupiter only once per orbit. And when it is close to Jupiter, it is traveling at around 50 kilometers per second. It's very, very fast. And so that is also how we have survived so long around Jupiter. So if we go in really fast, we collect our data, and then get out, and then we have a lot of time away from the intense radiation to send the data back and do remote observations from a distance. And so that's how we are able also to help with that.
And Rosaly, we have Moshark who asks, how much longer will Juno be active?
Oh, well, that's maybe more of a question for Dustin, but it's there are limits based on the amount of radiation that Juno can withstand, and and there is always the limit of funding as well. But we hope that Juno will be around for a while longer. And these missions, by the way, they are very well engineered, and they tend to last longer than we think. For example, Galileo lasted a lot longer. The Mars exploration rovers, again, lasted a lot longer than we expected. So we build them well, and we put a lot of work and thought into that engineering, because these missions are very expensive, and so if they last longer, you get more out of them.
Absolutely. And so I have a great follow up, talking about this incredible engineering. We have Taylor T69420 on X who asks, what kind of radiation hardening is used to allow probes to survive the Jovian system? Dustin.
So the quick answer to that is several hundred pounds of aluminum and titanium to protect all of the electronics. The Juno mission has what I call this radiation vault, and it is composed of titanium to protect all of the electronics that we put into Juno. And so that's one step. The other step is all of our spacecraft that we design have what we call redundancy in them. So if we get hit by radiation, or if we get hit by a particle or something that causes damage to a component on the spacecraft, all of the critical components of the spacecraft, there are generally two of them. So we have two radio communicators to Earth, we have two radios to Earth, we have two computers, two data handling systems, and all of these. So if one goes down, in fact, the spacecraft will autonomously detect that something's wrong with what's happening, and it will switch to the backup. And so we can either command that to happen, or if it happens and the spacecraft thinks it's going to end up hurting itself by trying to use the current device, it will switch to the other one. And so we have this what we call redundancy, and we also have the radiation hardening.
It is fascinating to honestly hear, just the engineering involved in these spacecraft missions. Dustin, can you tell us how long from maybe like concept design to build finish did it take to even come up with Juno?
I've been on Juno since orbit insertion, so it's been since 2016. Just prior to that is when I started. Before that, the mission launched in 2011, and the concept and design and proposal was many years before that. So these are decades long projects that takes a lot of time to design the mission, the concept, put it together, and build it, and then launch it. And once you launch it, you still have to wait a very long time to get to Juipter. And so this is often a decades long process.
Yeah. And so going back to this, always the radiation question and how we're protecting spacecraft against radiation from Juipter, could this technology be used to protect humans if we one day venture out there ourselves? Rosaly or Dustin for that one?
Well,
I
if we go to Europa or Io, we're certainly going to have to protect the humans. I mean, the radiation dose at Io would kill you in a day. So you would have to protect the humans very well. And I'm not sure what exactly you would use,
Yeah.
but maybe by then we'll have even better ways or better materials. Dustin, anything to add?
Yeah, I mean, when Juno flies by Jupiter, we get about 150,000 dental X-rays worth of radiation in a very, very short period. It's a lot of radiation, and so we definitely would need to protect. And right now we're using metals to do that, but as Rosalie mentioned, maybe there will be future materials that we will discover that will help us protect humans.
And so, you mentioned it like when talking about Juno flying by Jupiter, we have Swedgy on YouTube who asks, "What is the propulsion that is used on Juno, and how do you navigate between these moons and Jupiter?" Dustin.
So we use just standard on Juno. It's just what we call standard chemical propulsion. It's a rocket. We use combine fuel and an oxidizer together and burn and through the rocket nozzle, and that provides us thrust. Juno is a very elegantly designed mission in that we don't need to do a whole lot of that while we are at Jupiter. We used a lot of fuel to get there and to enter orbit in 2016, but that we're there, Juno is mostly on what we call a ballistic trajectory. So what we do is we fly the spacecraft, and Jupiter pulls on it, the moons pull on Juno, and that just naturally causes the spacecraft to keep flying in a particular orientation. Every orbit, we take analysis of what the spacecraft's position is, and we measure that by sending a radio signal from Juno to Earth at a given frequency, and we know when that was sent and what frequency it was sent at. And when we receive it on Earth at these massive antennas at NASA's Deep Space Network, we can receive that signal, and the frequency we received is different than what was sent. And so that tells us the spacecraft's velocity. And then we also know when it was received. And so if you know when the signal was sent and when it was received, that's the distance to the spacecraft. And so we measure what we call range and Doppler measurements to determine the spacecraft's trajectory. And then we can carefully navigate that spacecraft to where we want to go, relatively close to what that ballistic trajectory was. So we make little corrections every single orbit in order to maintain what we want to do for our science.
And so I want to take us back. We have a lot of interest coming in right now on Europa. And I have Carrie Ann on YouTube who wants to know, will there ever be an attempt to get samples from the plumes on Europa? Uh,
Uh,
Rosaly.
I, yeah, I can take that. That's a very interesting question. But the problem with plumes on Europa is that, well, first of all, we still have to confirm that these plumes are there, and they seem to come and go. So you can't really plan a sample collecting mission unless you actually know that the plume is going to be there for a long time. So in fact, we are doing a study at the moment about a sample collecting mission to collect a sample from Io, because on Io we know that there are some plumes that last a very long time. For example, one of them, the Prometheus plume, was active when Voyager flew by in 1979, and every mission that flies by, Galileo, New Horizons, Juno, everyone sees Prometheus being active. So that you can plan for, because it's a reasonable assumption that the plume will still be active.
Are you able to give us a little details on like how the sampling mission could work?
Well, you would have to send a spacecraft there. We have ways of collecting samples while the spacecraft flies through a plume, and then the spacecraft comes back to Earth, drops off the capsule, and then that's analyzed in laboratories. We can send very good spacecraft to the planets, but we can't send the kind of instrumentation that we have on laboratories on Earth. And that's why we have been collecting samples from asteroids, like OSIRIS-REx has come back with samples that are being analyzed now, and also the Hayabusa missions from Japan, and bring back rocks from Mars so they can be analyzed in laboratories on Earth.
And so, sticking with this topic of science of these two moons, Jay Word on YouTube asks, is there any tectonic plate activity on either Europa or Io? And if so, what kind of natural formations have formed due to it? Rosaly?
Yeah, I can take that. We see mountains on Io, but seeing mountains means there is some tectonic activity, but not plate tectonics. And on Europa, we see a lot of faults on the cracks on the surface, and people who have studied those cracks and the morphology say that okay, the crust has been cracked, and these pieces have moved around because they're floating on top of the ocean. So it's a little bit like you see on Earth with ice, for example, near Antarctica. But plate tectonics is something that we have not seen on any other body outside the Earth. So that seems to be very specific to the Earth, and is a very interesting question about why. Maybe because we need a lot of water on Earth for this to lubricate these plates, particularly in the subduction zones, one plate diving under the other. We need perhaps a certain thickness of crust relative to the size of the planet. For example, when Europa, the ice maybe is too thin. Although there have been suggestions of subduction on Europa, it's possible. On Mars, the crust is too thick. So you need that kind of Goldilocks for plate tectonics to take place.
And a great follow up, we have Universe on X who wants to know how thick is the ice layer on Europa? Dustin?
So we don't really know exactly for sure. That's one thing that we want to get a better answer to is how thick is it truly, but we believe it's on the order of something like 10 to 20 kilometers.
Wow. And so taking it back to Juno, what are the tools that Juno has on board? This is from Scientific Potato.
So Juno has a lot of instruments on board, and Juno's instruments were designed to look at Jupiter primarily. And so we have we call it the gravity science, which is what I do, which is tries to measure the gravity fields of the objects that we're flying by. Juno also has a microwave radiometer, which probes the atmosphere of Jupiter and also, of course, the structure of the surfaces on the moons. We also have a magnetometer at the end of the boom there. The one solar panel that looks a little different is the magnetometer, the magnetic field of Jupiter. We also have a couple of cameras. We have an infrared camera called GIRM, and we have a visible camera called JunoCam. There's also a suite of particle sensors, high energy and low energy particle detectors. And then we also have a plasma wave sensor instrument, which measures the electrical fields that the spacecraft is experiencing. And I think I might have missed one or two, but we also have another star camera that looks at the both Jupiter and the moons a little more detailed.
So all in all, though, we have a ton of science going on. And, we have Elle on YouTube who asks, given the signal delay, how are you able to control Juno? Dustin.
So Juno, we don't actively control Juno as if we're, we call it, we're not joysticking it. We don't send it a command and wait for it to do it, and then we send it back. It takes 45 minutes roughly for a signal that we send from Earth to reach Juno, and then another 45 minutes for it to come back all the way to Earth. So we can't actively control the spacecraft in that way. What we do is we send it a command, a sequence command, which generally lasts about a week, somewhere between 1 week and 4 weeks long, and it generally covers one orbit around Jupiter. And that command sequence instructs the spacecraft to do everything that it should do in that time period. So whether it be a week, whether it be a month, it does all those commands within that time period. And so every time while it's executing a 1 month plan or a 3 week plan, we're already planning the next one, and we're generating that set of commands. And so it all will happen on that cadence. There are times where we will command it more frequently, and those are for things like when we're doing these orbit correction maneuvers, or if there's an anomaly and we need to respond to it, we then send commands on a more frequent basis. But the general structure is it's largely just flying there and automated on this command set.
Wow. And so I have a follow up for you, Rosaly. It's Elevated One on YouTube who wants to know how powerful is Juno now compared to the Voyager spacecrafts, for example.
Well, I wouldn't say powerful is the right term. Voyager flew by. So Voyager was a flyby. It flew by the Juipter system, so the amount of data it could take was limited. Now, Galileo was a Jupiter orbiter like Juno, so Galileo got a lot of data, on Europa and Io. But the more recent spacecraft, of course, have more later technology and better instrumentation. So you always get a lot of improvement, and also the previous missions tell you what science questions you're trying to answer. So when you design the next mission, you're going like, I want to answer these science questions that we couldn't answer with the last mission. So you tailor your instruments to those science questions. And the science questions are always the starting point for any new mission or any new mission planning. Juno is gathering a lot of exceptional data on Europa and Io that Voyager could not get because when Voyager flew by, Voyager was a very exploratory mission. It didn't even know what it was going to find. And for example, with Europa Clipper, now we know a lot more about Europa from Galileo and somewhat more from Juno as well. And so the instruments were designed, for example, an radar to tell you about the thickness of the ice layer. And I will stress that Juno was not designed to look at the satellites. This was really a great opportunity. And I think Dustin can talk more about that.
Yeah, so Juno was designed to look at Jupiter, and in the original mission, we would not be actually flying by any of these moons. But because Juno has lasted so long, we now have this unique opportunity, and of course, we were going to take advantage of that to fly by these Galilean moons in order to look at them in more detail.
And so, talking again about just instruments and the science that is building on top of each other, we have a question from Justin on YouTube who wants to know what instruments and techniques could be used to check for life on Europa.
So, instrument-wise, there's no such thing right now as a life detecting instrument. Life is very complex on Earth, and we can look and detect life. But what we're actually looking for is what are the conditions to allow for life to exist, and do those exist on Europa, as an example? So we want to really look at, is Europa potentially habitable? So on Earth, we can go and look at all of these extreme locations, and in general, everywhere we look on Earth, there is life. And so what are the conditions on Europa, and are they compatible with the conditions that we know of that life could exist? And so we're looking at things like temperature, chemical composition of the ocean and the surface, the icy surface, to sort of to determine, what is it habitable? That's the real question we're trying to get at. And I really hope that a lot of instrument developers and engineers and future engineers can come up with these new ways to develop techniques to actually detect life.
And I have a great follow up to that for you, Rosaly. We have Connemara on YouTube who asks, what is being done to potentially protect the life that could be present at Europa?
Oh, we have what we call planetary protection. In fact, is a kind of international agreement that we're going to protect these worlds, and so we take planetary protection very, very seriously. Now, for example, some people ask why we killed the Galileo spacecraft by sending it inside Juipter, and we killed the Cassini spacecraft by sending it inside Saturn. And the reason was planetary protection. Galileo found that Europa could possibly have life, so we couldn't risk leaving it around the Jupiter system. One day it could crash on Europa, and the spacecraft had not been sterilized, so we thought the best way, the safest way, is to kill it. Same thing with Saturn, that the Galileo mission, the Cassini mission, found that Titan and Enceladus might have life. So again, in the end, we killed the spacecraft by sending it inside Saturn so that it would not contaminate. So I've been through two of those because I worked on Cassini as well. So maybe Dustin can talk more about Juno.
So for Juno, we of course have the same planetary protection requirements, and after our mission if the extended mission is over, we will have to do something to protect Europa and the other moons from our spacecraft, which was built, very cleanly, but we don't want to take that risk. We don't want to go to Europa in 20 years with these amazing new technologies that we would be developing and say we found life, and turns out we brought it there. We don't want to do that. So we will have to find a way to protect Europa, and we are already working on that, on what's the best way to prevent Juno from impacting Europa or contaminating it.
Now, Blue Lightning on YouTube has a great follow-up who wants to know, if we ever do discover life in Europa's oceans, what kind of life would we be expecting, Rosaly?
Oh, well, we don't know that, but we don't think that we would find whales. We're expecting microbial life. So, not whales, although sometimes we joke about whales on, on Europa. But no, the life would likely be primitive. We find life, for example, in the Earth's oceans, very deep around hydrothermal vents. So maybe that's something that we might find on Europa, but we're a long way from um, speculating what kind of life we would find there. But what's something that I find very interesting about life is that it usually finds a way. We find life in places on Earth that we wouldn't expect. And for example, decades ago, no one thought that life could exist in this deep, deep into the Earth's oceans until the discovery of these hydrothermal vents and life around them. And a colleague of mine once said, if no one had ever seen a fish, you wouldn't think that life could exist in the ocean. So we don't know what we're going to find, but that's what makes it so exciting.
Yeah, that's part of the journey. And so, Dustin, I understand you do study, the inner workings of Europa and the ocean. And so I have a great question for you from Strong Monty on YouTube, who wants to know, wouldn't the ocean of Europa already have plenty of oxygen if it is H2O?
That's a great question. H2O is water. We, as humans and life, can't breathe H2O directly unless you are something like a fish. You need to be able to have oxygen itself, and if you can actually dissolve oxygen in water, and so that also is where it comes into, is you can actually pull those oxygen molecules separately out.
And so why does it need more oxygen from the surface to be able to support life?
Well, we just think that's one of the mechanisms that oxygen can get into the ocean. We will learn a lot more from Europa Clipper when it gets there on all the mechanisms that may generate oxygen.
And so we've been talking a lot about these observations from orbit. And I have a question from Aldo Wakil Bandhand on Facebook, who wants to know, is there a way to zoom in really close on either of these worlds and see what's on the ground? Rosaly or Dustin?
So yes, if you have a camera that can do that, you absolutely can zoom in. And Europa Clipper has what we call a narrow angle camera, which is essentially more just like a camera with a telescope, and it can zoom in very closely on the surface of Europa. A lot of the resolution that comes out of pretty much any flyby from any spacecraft is how far away are you from the moon. And so the closer you get, the higher resolution image you can get. And so with Juno, we got about 350 kilometers from Europa's surface. And the JunoCam instrument took many amazing photos of the surface at very high resolution in certain regions to help fill in the gaps, so to speak, of from what we had previously. And Europa Clipper is going to get even closer to the surface, so we're going to really be able to zoom in and see very, very high resolution images.
Wow, and we received some pretty high resolution images recently, right, from Juno with Io. Um, and so I understand there's a public engagement component of this mission, right? Dustin, could you talk a little bit
Yes.
about JunoCam?
So JunoCam is an instrument that's a camera. It's not too dissimilar actually from your cell phone's camera in a way. And what it does is it takes pictures of the various moons and Jupiter itself. But what it does is as soon as those images come down and are transmitted back from Juno to Earth and are decoded at the Deep Space Network's telemetry into and sent back to our computers here at JPL, they pretty much go straight up to the internet, to the Mission Juno website, where anybody can download them and process them into, taking
Wow.
creative approaches, the scientific approaches to really piece out, all the different channels and all of the components of the JunoCam data and make their own images and post them back to the website.
Now, Rosaly, we have Peter on YouTube who wants to know what percentage of Jupiter's moons has Juno mapped? How many has it observed?
Well, Juno has obtained images from Io, Europa, also Ganymede,
Hmm.
and some of these images filled in gaps that we didn't have at sufficiently high resolution from Galileo, although they didn't get as much data as Galileo did, they got very, very useful data, particularly for mapping, and we use images to map the geology of the surface and the different terrains. It's really been a gift that the Juno extended mission was able to get such images of the satellites and also other data. Justin mentioned microwave radiometer, and I collaborate with the GRAM, an Italian instrument that's a thermal infrared instrument. And again, we got amazing data from Io. So it's really been an amazing gift that we use Juno to look at the moons.
And so you had mentioned Ganymede, and so I have a great follow-up question for you. Stephen Jackson on Facebook wants to know, will there be any additional observations of the largest moon, Ganymede? And I believe NASA has a mission called JUICE that will look into this, right?
I'll let Dustin answer that question, but I just want to say that JUICE is an European Space Agency mission. NASA has instruments on it, so there is a lot of collaboration, but it's actually an ESA mission, and it is going to go to the Juipter system and eventually orbit Ganymede. So it's going to really focus on studying Ganymede, but we'll also get some images of Europa and Io.
Amazing. Anything you'd add, Dustin?
So Juno did a close encounter with Ganymede in 2021 in the summer, and we got some really nice data from that. We won't be able to go back, unfortunately. So we had the one shot at seeing Ganymede with Juno, but as was mentioned, the European Space Agency JUICE mission, which there are NASA components on, will be looking at Ganymede in very detail.
And so I have a fun question to follow up on. We have IDLS on YouTube who wants to know, where did these two moons, Europa and Io, get their names from? Rosaly?
Well, those are names from Greek mythology. In fact, Jupiter was the king of the gods in Greek and then Roman mythology. And he Let's say that he was, a bit of a philanderer. He wasn't particularly faithful to his wife, and his wife, in fact, was called Juno. So
Oh,
the
wow.
moons are named, yeah, the moons are named after some of his lovers. Uh, and uh, and poor Io was a nymph that eventually got turned into a cow by Juno.
Oh man, that is a fun fact. Thank you for that, Rosalie. And so I want to take it back to the science of the two moons. Again, we've got a lot of interest coming in for Europa. And so we have Robust Brain on X who asks, do we know what the planetary core is made of on Europa? Dustin?
So we believe Europa has a solid core composed of what we call, it's more rocky elements, what we might
Mm.
be more used to. Is it the same as the center of our Earth? Maybe, but probably not. And so that's one thing that the Europa Clipper mission will be doing is mapping out the interior structure of Europa. How many layers are there? How deep is the ocean? How deep is the ice crust? And how big is that, the core of Europa?
And Winespring on X wants to know, where did the ice come from on Europa? Rosalie?
Well, water and ice are very, common elements in the solar system. So it really came from the solar nebula, from the formation of the Jupiter system. We think that those moons were formed in the same part of the solar nebula as Jupiter. But Io has no water. So they ended up very different, which is interesting. But again, if we look at our solar system, the planets are all very different.
And so my next question is from Miss Land's classroom. We've touched on this earlier, but for those just tuning in, would NASA be able to create a spacecraft or a machine to check for life under the ice layer on Europa? Dustin?
Yes, that is certainly possible, and that could be a potential follow-on mission to the Europa Clipper mission, where we would design something to land on the surface of Europa and take samples directly and do what we call, in situ measurements of, what then you can use, direct measurements of the ice, and potentially if you land in the right spot, drill through and get water samples, and that would be very interesting. Data in order to determine, habitability or life.
And so I have another follow-up question from Miss Land's class, a great one for both of you. What would you say is the most interesting data or images that Juno has been able to collect? Rosalie, we'll start with you, and then would love to hear your thoughts, Dustin.
Well, of course, I'm prejudiced. I love Io, so I think that the images of Io were the most interesting
Mhm.
that Juno ever collected. In terms of scientifically valuable, you can argue that Juno was a mission to study Jupiter, so it found a lot of new things about Jupiter itself. So the moons are kind of like a bonus. Uh,
Mhm.
as I said before, the mission was not designed to study the moons. But I think that the images we got of Io, not just the camera images, but the data from GRAM, for example, has shown us that Io has a lot more lava lakes than we knew of from Galileo. And I'll let Dustin give his opinion.
Yeah, so that's always going to be an opinionated response to a question like that. And
We're ready
what's
for it.
what's the most interesting data? I would say we're all a little biased in that way, so I'm going to actually choose what we discovered on what the gravity science of Jupiter, which determined the interior of Jupiter, and that's it was not what we expected at all. We see that the zones and belts around Jupiter penetrate very deeply into the surface. It's not just it's not just like a weather layer. These zones and belts, they penetrate 3,000 kilometers into the structure of Jupiter. My favorite image is actually what was just shown there, which is the pole. We never were able to really look at the pole of Jupiter, and Juno flew right over the pole. And as soon as we got those pictures of over the
Wow.
pole of Jupiter, it's just astonishing. You can see all of these cyclones or
Wow.
anticyclones just visibly right there on the surface. That's not something that you can see from Earth. You have to go there and put a camera on the pole in order to see it. And that was just mind-boggling to me when I saw that image.
And I have, again, another biased, quick final question for you both from OV101 Enterprise on X, who wants to know which one of the Galilean moons is your favorite. Dustin, we'll start with you. Rosaly, I think we could guess that one.
Well, I'm going to have to go with Europa on this one. It's an ocean world that we can access, and we're planning a mission to it. And there's going to be so many interesting data that come out of that. If it's a strong candidate for their potential to be life, and I just love looking at the surface of it. It just looks, it looks so alien and foreign, and you see all these cracks and ridges, and I that's my favorite Galilean moon.
And Rosaly, what about you?
Well, well, of course, Io is my favorite moon, and hey, it looks like a pizza. In fact, it was nicknamed the Pizza Moon. So if you like pizza, you like Io, it's just for volcanologists is
Mm-hmm.
absolutely heaven. We have so many volcanoes and so many weird formations that you don't see anywhere else in the solar system, and a surface that has no water, and but a lot of sulfur dioxide. So very different materials from what you see on Europa, Ganymede, Callisto, and the others, it has this enormous plumes up to 500 kilometers that erupt from the surface. So there is something exciting happening on Io all the time that makes mapping it quite difficult because you look at Io with one spacecraft and then it changes. In fact, it changes in months. We can have a big eruption that deposits a lot of material on the surface, and you think, oh, it doesn't look like it used to. So there is always something happening on Io.
Yes. Well, thank you both so much for joining us today. Unfortunately, that is all the time that we have. But again, we really appreciate you taking so many questions from our viewers online.
Thank you for having me. It's been such a pleasure to talk about it.
Thank you. It's really been fun. So keep looking at the websites. Juno will do a lot more.
Thank you again. And thank you to everyone who joined us online. We hope you enjoyed learning more about the fascinating worlds of Europa and Io. If you'd like to stay up to date on the Juno mission and its study of Jupiter's moons, visit go.nasa.gov/Juno or follow NASA Solar System on Facebook, Instagram, and X. If you enjoyed today's show, you can check back with us tomorrow, March 8th at 11 a.m. Eastern. Dr. Lori Glaze, our head of planetary science at NASA, and U.S. Poet Laureate Ada Lamont will be taking to the stage, kicking off the South by Southwest Festival, chatting about our Europa Clipper mission, which is launching later this year to see if Jupiter's icy moon has conditions suitable for life. Visit go.nasa.gov/Europa Clipper SXSW to watch live, and you can stay tuned for a special surprise. Thank you all, and see you next time.